Well, hello everyone. Welcome to another installment of the NAPA Echlin Education Series. My name is Darren Beanard. I'll be your instructor today. Today's subject is turbochargers. But we've got a special treat today because Ryan and Chris happen to be out in the shop today getting ready to do a 6.7 liter Cummins turbocharger installation. So let's check in with them and see how things are going.
Okay, hey, thanks Darren. Chris and I are here in the shop today. We're doing some installation. We're doing a little bit of testing. We've been playing with some calibration on some turbo actuators here. Chris is going to do an installation on this 6.7 Cummins today. So before you get too far in your presentation, Darren, we'll just share a couple little tips here. Yeah, I can't stress the importance of when replacing a turbo, use all the gaskets, all the components that come with it. On these Echlin turbos, we take pride in installing every one of these, not each individual one, but every model, and making sure that we've got all the components required to do the job in the package. So I encourage you to use those. Also, we're going to want to make sure that we pre-lube this turbo here. First off, on the truck, we need to diagnose the original failure and make sure that we had good oil flow on that one. And then we want to make sure that we put fresh oil in this turbo, and then we'll install it on the truck. When we eventually do start the truck, we're going to let it idle for a couple minutes just to make sure we got good oil flow through it before we start redlining this thing and seeing if it's working. Obviously, every time we replace turbo, we're going to go ahead and replace the air filter as well. We want fresh air coming into this thing. And if there's been any debris in there, we want to take a look at the intercooler and make sure that there's no debris that came out of the old turbo or even oil, right? I mean, quite often we see a lot of these things just full of oil, and it causes problems with the new turbo. So in some cases, you might have to flush the charge air cooler or the intercooler. So Chris, any tips that you can share from your diagnostic days?
Yeah, like Ryan said, so we want to make sure that we verify we've replaced the air filter, do an oil change with the oil filter as well. We want fresh oil to lube this new turbo. And if we have an electronic actuator, we want to make sure that we're following any calibration tips that may be, followed from service information. And we want to look over the turbo design, make sure that it's applicable to the vehicle. And if there's any adjustments required for the actuator for the wastegate, sometimes there are, and other times there are applications that we are not supposed to adjust that. So we want to follow service information of what we have to do with that.
Right. Let's not be adjusting to get more boost or more power out of it, but there are some we do have to follow up with. And I'll share a self-depreciating story here. Recently, I'm trying to diagnose an actuator problem. There was a blown fuse involved, and so don't forget about that. It's an electrical device that needs power, ground, and communication. Chris has had some case studies where the wires were rubbed up against the engine block, shorting out the CAN communication lines. And so we see a lot of stuff that people don't think about until after they've replaced the turbo. Let's go ahead and think about that before replacing the turbo. Exactly. So, all right. Well, hey, back to you, Darren. We're going to get working on this, and we'll see how far Chris can get in the next half hour here.
Well, thanks, Ryan and Chris. We appreciate very much you giving us the opportunity to take a look over your shoulder while you do that turbocharger. We'll be checking back in just a little bit to see how far they've been able to progress. Of course, today's class is turbochargers, and in recent years, manufacturers have been incorporating turbochargers into their designs to increase efficiency, to get more power out of a smaller power plant. And so today, we're going to see how that affects the technician, how that you'll have to deal with the various issues that you're going to encounter when it comes to diagnosing and repairing turbocharger issues. So let's get into today's class. So before we get started, I'd like to bring out our mission statement. It is to help the aftermarket automotive technician in dealing with these very highly technical systems to help you to be able to perform accurate and efficient diagnosis and proper vehicle repair. That is what it's all about. If we can help you do that, it's going to help all of us. So that's our thinking on the matter, and so we appreciate very much the opportunity to be able to bring this information to you today. So what are we going to discuss? Well, as I said, we are going to look at these the issues that technicians face when they're dealing with turbochargers. So we're going to look at turbocharger operation, we're going to look at wastegate control, we're going to look at variable geometry control. There are different types of systems that will regulate the turbocharger itself. So how do we control that? That's the wastegate or the variable geometry. We'll look at those systems. And we're going to incorporate diagnostic principles throughout today's class. So that that will help us all in dealing with these turbocharger failures. Now, let's begin with a case study. We have this 2014 Chevy Cruze. It's got a few miles on it, as you can see right there. And the problem that this vehicle has is that the check engine light is on. The customer's complaint is that it has a severe lack of power. In fact, it's so bad, the customer actually had the vehicle towed into the shop. So it came in on a rollback. Well, the technician raised the hood. Now, of course, you can see he's doing some stuff there under the hood. He took this picture after he had already started kind of poking around under there. But prior to all of this, he did an inspection, and he didn't see anything out of place. There wasn't anything unusual or anything like that. So our technician scanned the ECM for codes, and he found two. A P0299, engine underboost. Sounds like it may be related to our underperforming engine, right, or lack of power. And we also have this P2227, which is a baro sensor performance code. Well, the technician thought about it and figured that, you know, that baro code, that 2227, is probably maybe some sort of a side effect of whatever else is going on. Maybe he focuses attention there on that P0299, that engine under, or that turbo underboost code. So he took the vehicle out for a test drive, and as I said, remember the customer had it towed in, so he wasn't expecting much. He didn't get much. When he got out there on the road, he actually tried to drive this car, and it was very difficult to drive. In fact, if you'll notice here, we've got these markers on the scan data here. And as he's driving it, you can see he has his foot buried into the carpet. The throttle position sensor is at 100%, well, 99.9%, but that's 100%, right? And this thing is achieving a whopping 16 to 43 mile per hour increase in 36 seconds. Yeah, this thing won't get out of its own way. This thing is not, it has no guts at all. Well, the technician, you know, he's had a lot of cars that have this type of problem. He just knew what was wrong with it. His gut feeling is this thing needs a catalytic converter. And maybe he's right, you know, because a catalytic converter is among a long list of possibilities. When you have a lack of power, you know, you've got a lot of different things that could possibly be causing a lack of power. He just knows this thing needs a catalytic converter. All right, well, that's fine. So guess what he does? He recommends that to the service advisor. Service advisor calls the customer. Customer says, oh, okay, let's put a catalytic converter on it. Unfortunately, this car's not fixed. So what do we do now? We've just spent a lot of money, a lot of the customer's money, and we have no result. What are we going to do about it? Well, we're going to take a step away from this car. We're going to come back in the end. We're going to fix it, and we will see what was really obvious, what was wrong with the car. All right. So in the meantime, let's discuss how a turbocharger operates. Now, to explain how a turbocharger works, we're going to use this basic turbocharger illustration. Now, we've deliberately left out some key parts of the turbocharger assembly so as to be able to concentrate just on the basic principles and the basic parts, the internals, the basic internals of a turbocharger. So what do we have here? Well, we have a turbine and a compressor. Now, the turbine will be driven by exhaust gas pressure that's generated by the combustion process. Now, that energy is going to be diverted to the turbocharger's turbine, as you see here. Now, what's going to happen? Well, the turbine will spool up, which in turn spools up the compressor. Now, the compressor is going to then take filtered air, compress it, which not only increases the air density, but it also causes the air to heat up. That heated, dense air will then, or compressed air, will then be sent through a cooler, in this case a charge air cooler. Maybe you've heard the term CAC, C-A-C. That's what they're talking about. So we're going to send that compressed heated air into that charge air cooler, which then will cause that air to have a good portion of its heat removed, so we're going to cool it. Now we have cooled compressed air that's sent into the combustion chamber, where its increased density amplifies the combustion event to deliver greater horsepower, and the process starts all over again. Now, turbochargers have become instrumental for car manufacturers in their attempts to get as much power as possible from a smaller engine, which is going to lead to overall better fuel efficiency and performance. but there are limits to how much power increase we can allow a turbocharger to provide. Otherwise, there could be an undesirable result. Therefore, there has to be some type of control for the turbocharger so that we can maintain the proper amount of horsepower increase without serious consequences. Now, this leads us to our next discussion point. How do we control the turbocharger? Well, there's actually a couple of methods. One is a wastegate. The other is by a variable geometry design. Let's start with the wastegate system. Now, in a wastegated turbocharger control system that we see here, there is a valve known as a wastegate right there. Now, when the wastegate is closed, all of our available exhaust gas pressure will be directed toward the turbine. And this is going to allow for maximum turbine spool up according to whatever available exhaust pressure there is at that moment. Now, to control the turbine speed, the wastegate, once again you see it here, that wastegate will be opened. It's going to allow some of the exhaust gases to bypass the turbine. The amount and duration of wastegate opening will be varied to allow for the appropriate amount of turbine speed regulation. So that brings us to the next question, or the next point that we're going to talk about. How is this wastegate opened and closed? So let's look at wastegate actuation systems. There's actually a number of different types of wastegate actuation systems which we will now look at. Now, here's a list of the 4 main types of wastegate control. They are pressure actuated, normally closed, pressure actuated, or rather vacuum actuated, normally closed, vacuum actuated, normally open, and electrically actuated, normally closed. Now, we should note there could be other types that manufacturers may currently use or may use at some point. These are the 4 main types of wastegate control systems that are out there. So let's start with the pressure actuated, normally closed system. Let's see how it works. Now, here's an illustration of a typical pressure actuated, normally closed wastegate system. If you notice, we've included some additional components that many manufacturers are going to use to increase performance and also offer control there to the PCM, to give the PCM the ability to offer some control. And we're going to explain these different parts here shortly. But now, as we just look at just the pressure actuation portion of the system, we see here as the wastegate rests in its normally closed position, it's held there by a spring-loaded actuator. You see that spring-loaded actuator right there. Now, there's a spring in here that is going to cause that wastegate to be held closed. Now, there's a control line. See it there highlighted in red, that control line? The control line will be fed by boost pressure. And of course, it connects to this spring-loaded actuator. Now, as pressure builds in the control line, as boost pressure increases, the increasing pressure acts on a diaphragm in the actuator, during which time there's going to be a tug of war going on in the actuator. And so we're going to have that, that tug of war will be occurring until finally, once control pressure achieves a certain level, it's going to overcome the tension of the spring, and this is going to allow for the wastegate to open, which results in exhaust pressure being channeled away from the turbine. Thus, turbine speed is regulated, which results in a controlled boost. Now, what about the solenoid, right here, that solenoid? I haven't addressed that yet. And also the PCM, you see right here. What about all of that? Well, now, many manufacturers are going to include this in their wastegate control to allow the PCM to modulate when and how much control pressure actually reaches the actuator. This is going to allow for the wastegate to remain closed or have a regulated opening so that the turbocharger output can be higher than it would otherwise be. Now, in this way, the manufacturer can maximize turbocharger output, giving us an even greater amount of performance. Now, of course, PCM is going to have to take into account factors like engine coolant temp, because, you know, I mean, if our engine's overheating, we don't need to be allowing for excessive or extra boost, or even maybe any boost at all. Knock sensor. We don't, if we've got spark knock going on, again, that's going to affect the PCM's decision making as far as how it's going to regulate that wastegate. MAP and other inputs, they're all going to be used to make sure that it's safe to allow for an increase in engine power output. Now let's take a look at a normally closed vacuum operated wastegate. You can see here in this illustration, or in this arrangement, we have this, once again, this actuator that is spring-loaded closed. So at rest, in the closed position, in the absence of any other influence, we're going to have that wastegate being pulled closed, and so we'll have maximum available exhaust pressure. Whatever we have, whatever exhaust pressure there is available, it will all be directed toward the turbine. The PCM is going to control a solenoid so that when the PCM sees fit to regulate turbocharger output, it's going to use this solenoid right here, this vacuum control valve as they call it in the illustration, to apply a vacuum to the spring-loaded actuator. And in this way, we're going to pull that wastegate open, or to some degree. But this system actually gives the PCM full control over the wastegate actuator. It does not have to be dependent upon the availability of boost pressure. The PCM is in full control. It can open that wastegate anytime it wants to. Now, it's noteworthy that there's likely going to be some kind of a vacuum sensor somewhere in this circuit right here that will be used by the PCM to monitor whether there's sufficient vacuum pressure, or I should say vacuum present, to properly operate the wastegate actuator. Data from this sensor may be available to you in scan data. So that information could be very useful when you're diagnosing a turbocharger control fault. Now let's look at the vacuum actuated, normally open wastegate control system. Architecturally, this system looks just like the previous system. However, the difference is that this system operates oppositely to that previous system we just looked at. As the wastegate actuator is at rest, once again, when there's no other influence on the system, no vacuum being applied, there's an internal spring in the actuator that is going to hold the actuator arm in a position that causes this wastegate right here, the wastegate, to be open. And that means if you don't have any vacuum present, then you have no boost. Now, when the PCM calculates that boost is warranted, it's going to energize this vacuum control valve, and it's going to allow vacuum then to reach the actuator. This will cause the wastegate to be pulled closed. Now we're going to have boost. Once again, just like the previous system, this allows the PCM to have full control over wastegate actuation and boost. Now you may be wondering, well, now where does this vacuum come from? Because, we're talking about a turbocharged vehicle here. We're talking about a turbocharged engine. And there's not always vacuum available, is there? Sometimes on that manifold, and I'll say a good portion of the time on that intake manifold, we have pressure above atmospheric. So we don't have vacuum. Well, manufacturers have figured out how to provide a readily available source of vacuum for the operation of these types of systems. One method that we see here on the left is a GM example. There's a vacuum reservoir that's actually attached to the bottom of the intake manifold. This is going to retain vacuum during periods of time when we have manifold vacuum available, and then we are going to then have a vacuum source when manifold vacuum is not available, when our manifold pressure is above atmospheric. Another method that's commonly used is to have a vacuum pump. The vacuum pump could be mechanical, like the Ford example we see here. I think that's a 1.5 liter EcoBoost. Or it could be an electric pump. Whichever they choose, they could do. So we could have that vacuum pump, or we could have a reservoir. Finally, let's now move into the last wastegate control system that we're going to highlight, and it is this electric motor type. Now, this one that you see here, this is from a 2017 3.5 liter F-150 EcoBoost. This one has a normally closed system. So this electric motor right here, you see that arrangement, will be holding that wastegate closed. But there's no reason to think that a manufacturer couldn't engineer a system like this to be normally open, right? We just see that we have this normally closed system, but it might at some point could end up being the other way around, where it's normally open. That said, what's going to happen? How does this thing work? Well, that's pretty straightforward, isn't it? We have an electric motor actuator that the PCM is going to use to operate the wastegate. Now the system, as we said, is currently shown with the wastegate in the closed position. Now when the PCM determines that there is a need to control boost pressure, it's going to use the electric motor to open and regulate the wastegate. And this is going to allow for very precise control of boost pressure. The PCM can move that motor to any position it wants to, and we could fully open that wastegate, or we could partially open that wastegate to any position that it wants to in order to regulate that turbine speed. Now here's a schematic from that 2017 Ford F-150 with a 3.5 liter EcoBoost, and this truck is of course equipped with the electric actuator wastegate control. And we can see that each turbocharger, there's two on this truck, one on each bank, we can see that each one has an actuator motor that has two reverse polarity motor control circuits. And so I'm just going to highlight this one right here. You see that we have those two circuits, and of course they're both handled by the PCM. So the PCM can reverse polarity of that motor to drive that motor in either direction that it wants to. Now we also have a position feedback. So the PCM can monitor the position, the current position of that motor. That being the case, there will be some scan data that will be available for you. And so if you go into your scan tool and you want to look at this, well, we can see that we have a couple of PIDs here that are useful for turbo diagnostics. The bottom two right there, we see the second one up from the bottom gives us the actual commanded or desired position for that wastegate. The PCM currently says I want it at 47.63%, and you can see the position sensor right here, that voltage, 2.38 volts, would be reflective of that position. And so, as a matter of fact, if we look at the graphing, the graphs, those two graphs, they follow each other. They're trending together. So if you're diagnosing a fault, it might be good to graph those to see that they are trending together or not. It may be that the PCM is making a command, and it may be that the motor is not following the command for whatever reason. And so that would be useful for diagnostic purposes. Now one last part that we want to show you in regards to the wastegate system is this bypass valve. And that's going to be found on many applications. Now this particular device, it's going to reside on the boost side of the system, and it'll be used to provide an escape route for boost pressure during periods of deceleration. So just picture you're going down the highway, and you might be throttling pretty heavily, and you've got boost, your turbo's active. Then what happens if you take your foot off the accelerator pedal? And of course the throttle plate is going to close during that deceleration, isn't it? And of course we have electronic throttle control, so it's not necessarily going to slam close, but it is going to close. Now what happens though to that boost? You get all that boost pressure that we built up in that system. What's going to happen to that? Well, it's got nowhere to go unless we provide it with an escape route. And so that being the case, we have this bypass valve, which will provide an escape route for that boost pressure that will actually cause that boost pressure that we no longer need at the moment to be rerouted upstream of the turbo, so that it is that we have a relieving of that boost pressure, so we don't end up with some adverse consequences. We could actually, if we didn't have that, we could actually cause damage to the turbocharger. But also that device, that bypass valve, also provides a method of perpetuation of the compressor spin, so that then when we once again accelerate, we don't have as much or any subsequent lag that could occur. So there's a number of benefits to that bypass valve right there, and so you'll find that on manufacturers' turbocharger designs. Now let's move into the variable geometry turbocharger. From this point forward, we'll refer to it as the VGT turbo. Now here we see three examples of VGT turbos. Now there's many, many more out there, but we just wanted to show you some examples. At bottom left is a Duramax L5P VGT turbo. At middle top is a Ford Powerstroke 6.7 liter VGT turbo. And at bottom right is a Cummins Wholeset 6.7 liter turbo, which, as we said earlier, is one that Ryan and Chris, they're out there in the shop. I can hear them going at it right now. They're actually busily involved in a replacement. We're going to, as I said, we're going to check back in with them in just a little bit. Now, there's a couple of different types of control for the variable geometry, or VGT, within these turbos. One is a solenoid that sends oil pressure to a piston-like mechanism, which will drive the VGT position. The other is a module attached to the turbo assembly, which uses an electric motor to control the VGT. So let's take a look at both different types. Now, this particular one, this is the one that is going to use a solenoid. It drives, will send oil pressure to a piston mechanism. And that mechanism will then move something referred to as a unison ring. So we have this unison ring that has a series of vanes located around the circumference of the unison ring. Now we mentioned that there would be some type of control that's going to change the clocking or indexing of this unison ring. And as the vanes move within the helixed groove in the ring, they will change their angle, thus opening and closing. So as we look at the illustration here on the left, we see these vanes are in their closed position. And of course, again, that is according to the indexing or the clocking of that unison ring. In this position, exhaust flow will be more restricted, but we're going to be directing maximum exhaust pressure in on that center turbine, that turbine that's in the middle there. So the turbo is going to spool up. Then, as we want to regulate the speed of the turbo, we're going to then re-index the unison ring, which will cause the vanes to open to some degree. The exhaust flow becomes less restricted, but now we're going to allow pressure to be diverted from the turbine, so in that way we are going to regulate the speed of that turbo. So that unison ring is actually going to be engaged in a very active movement. It's going to be continually moving back and forth, back and forth, back and forth as we spool that turbo up and regulate the speed of that turbo. So how do we control that unison ring? Well, here's an example of the solenoid oil pressure controlled VGT. This is on an early Duramax. This is from a Duramax LB7. And so the PCM will be controlling that solenoid. That solenoid will have a spool valve that will be used to direct oil pressure into this hydraulic piston mechanism. You can see that piston is then in turn going to drive a rack style gear. It's meshed with a cam style gear. That will then in turn drive the unison ring using that control rod that you see right there. Now on the Duramax, there is a position sensor that will ride on an eccentric that's part of that cam gear that you see right there. Now other manufacturers such as Ford may not necessarily use a position sensor. Many other manufacturers may just use calculation, or they may, the PCM may calculate the position of the turbocharger VGT using other inputs. But if there is a position sensor, that would also be more additional data that would be available to the technician in scan data. Now some VGT unison ring designs will use a module known as a VGT actuator to control the VGT position. Rather than using the oil pressure solenoid mechanism, this particular setup will actually have an actuator that has a motor. That motor will drive an actuator rod, which will then in turn move the mechanism. Now we're looking at both the front and back sides of this particular turbo. This is from a Duramax L5P. So the actuator is actually a module. There's logic in here that will actually communicate with the ECM over a private CAN bus. And so this actuator module will receive commands from the ECM. It will respond back to the ECM with diagnostic data. Now what about the sliding plate style VGT, as in the case of the Cummins 6.7 liter? Well, this is a different type of arrangement for sure. In this case, we have an electronic actuator module that's going to house an electric motor that's used to drive an internal VGT mechanism. Now, I have a little video here, shows the movement of this particular style of VGT. As you can see, that's quite a bit different than the unison ring vane setup. We're going to have this VGT plate that will slide in and out, and as it slides out, we'll have exhaust pressure directed in on that turbine right there, and as it slides back out again, we're going to regulate the speed of the turbine. Now, I kind of liken this to a movable squirrel cage. And so in that case, again, we're going to be directing oil pressure either directed toward or away from the turbine as the vane plate moves back and forth. Now, this VGT control actuator that you can see in the background there, that is actually going to piggyback on the turbo assembly itself, and as I said, it has a gear motor that drives this, and there is logic in there. It's actually a module that will be communicating with the ECM over a CAN bus. Now here's a look at the schematic or the arrangement for this, the communication arrangement between the PCM and the VGT actuator. We have this CAN link right here, that's controller area network link between the PCM and the VGT actuator. There is power and ground also being supplied to the actuator from the PCM. Okay, let's go back to the opening case study that we promised that we would fix in the end. Because remember, we had that dilemma. We had that car that we spent all that money on and we didn't fix anything. Well, just to refresh your memory, here it is. It's that 2014 Chevy Cruze. Check engine lights on. We have a severe lack of power. So bad the customer had this thing towed in. We had two codes. Remember the codes? P0299, engine underboost. P2227, the Barrow code. Of course, the technician decided that the Barrow code was maybe a side effect of everything else. So let's focus on the engine underboost code. You remember he took the car out and he drove it. He floored it and it wouldn't hardly get out of its own way. He replaced the catalytic converter and did not fix the car. So obviously something was missed. Our technician here needs a new plan. So he decided to re-examine the scan data. Well, taking another look at the scan data and thinking about what can cause a lack of power. Certainly a lack of fuel could cause a lack of power, right? Well, that's one of the things that could certainly cause it. We need to make sure we've got plenty of fuel. Well, when we look at the scan data, we find that our oxygen sensor under acceleration is switching, which on this particular car is normal. If it were going lean, which it is not, that would indicate a lack of fuel. It looks like we have plenty of fuel. That's not the problem. That tells us a couple of things too. It tells us not only do we have good fuel supply, our fuel pump is delivering a good amount of fuel, but also tells us our fuel control is working. Maybe the mass airflow sensor is likely not the problem either. Well, looking further into the data, he noticed that with the throttle fully open right here, we're only getting a engine load calculation of around 48%. You see, we should be probably at least 80% or more on this particular car. So that's a problem. There's an issue. Now, when we come to this concern, or we have this particular type of issue with load calculation, it usually comes down to one of two main possible causes. Either one, we've got a mass airflow sensor that's not properly calculating or helping us to calculate engine load, or two, we might have a breathing problem. Well, I think we already mentioned that the mass airflow sensor had already been eliminated as a cause because remember, we had good fuel control. Something else is going on. We have a breathing fault, most likely. So looking more closely at the data, he realized the MAP sensor indicated that we have a intake manifold that's under a vacuum when it should have been under boost. If you look at that pressure right there, see 9 psi? at key on engine off, when we first cranked the engine up, we started at around 14.5 psi of atmospheric pressure. We're below atmospheric pressure by about 5 psi. That's a vacuum. You see, we should be above atmospheric pressure if our turbocharger is working. The turbocharger is the one that's responsible for supplying the boost pressure that we don't currently have. So our technician decided to take a close look at the turbocharger itself, and when he did, he noticed that when he took the oil supply line off of the turbocharger, he found that this thing was completely clogged with solidified oil. This meant that the turbo would have been oil starved. This created the perfect situation for turbocharger failure due to a lack of lubrication. Well, he removed the turbo, which, well, in this case, on this car, meant we got to take the exhaust manifold off because it's part of the exhaust manifold assembly. And you notice what he found? Yeah, we see the turbocharger is completely shot. This thing is destroyed. This car needs a new turbocharger. So as I said, that means we got to replace the entire assembly. That includes an exhaust manifold. It comes as one nice, neat little module package there, complete with a free exhaust manifold. So their technician also replaced the oil feed tube and other needed parts, whatever else was needed. And afterward, now it's all flowers and rainbows. This thing is running great. We have plenty of power. You can see now he's accelerating. He has, once again, his foot buried in the carpet, but we are accelerating nicely. Why? Because we have plenty of boost. You can see that we have what we expect to have on a turbocharged vehicle. All right, well, we've fixed this one, but what did we learn from this case study? I would say, from my own perspective, I would say let's not overlook what scan data is telling us. Really, the issue was right there all along, but our technician probably failed to look deeply enough into the scan data. And our scan data will be very, very helpful, especially when we're diagnosing these types of issues. All right, well now before we wrap things up, let's go back to the shop. Let's check in with Ryan and Chris and let's see how things are coming along.
All right, well, thanks, Darren. Great information as always. I've been kind of behind the scenes here, watching a little bit about what you're doing and supervising Chris here. So you can see where he's at so far. So Chris, just share with us where you're at.
Yeah, so we've gone ahead and removed the air intake piping. We've also disconnected and removed the passenger side battery so that we don't have an accidental arc or anything like that. We've also got our oil feed line disconnected, and we can take the connection off here at the turbocharger itself. We've also gone ahead and removed the electrical connectors for the harnesses that go to the turbo, and we've also removed the drain lines at the bottom as well as draining the coolant prior to doing anything else on the turbocharger so that we're not just draining coolant everywhere. So we've got everything drained on here. We'll continue kind of disconnecting things, and essentially all we've got to do now is remove the turbocharger from the exhaust, and we should be able to have the unit out of the truck.
Awesome. And so I see you removed the oil feed line, not just from the top of the turbo, but you removed it from the engine block. Any particular reason for doing that? Yeah,
so these are kind of a tight fit at times, and sometimes the fitting will get stuck. So I'll remove it from here, and then I've got some room to work with the fitting underneath. So at times this feed line can get stuck on this nut, and I may have to kind of have some room to work. So we'll undo it there, and now I can actually grab the nut underneath.
Awesome. That's the voice of experience right there. Great, helpful tip. I've had that a couple times where it once twists the entire assembly. Now you're up against the exhaust, and you might snap that line off or something.
Exactly.
I guess it's not the end of the world if somebody's going to replace that line at the same time here. But while you've got it off, certainly we want to make sure that there's no debris in it, make sure it's clean, reposition it on the new turbo, and then we can start the reassembly process. So, all right, we'll send it back to Corey and Darren in the studio there. Thanks again, guys. Great presentation.
Awesome, guys. Thanks, Chris and Ryan, for letting us look over your shoulders on that turbo replacement. Looks like you've made a lot of headway in 30 minutes. That's really good. So, folks, what did we discuss today? Well, we discussed turbocharger operation. We looked at wastegate control. We looked at variable geometry control. And we even incorporated diagnostic principles into today's class. Well, this brings us to the end. All right, Corey, do we have any questions?
Yeah, it looks like, Darren, we do have a couple questions. I tried to answer a few in the background here while we were going, just because in the spirit of time, I know we've kind of gone over a little bit here, but a few good ones that I wanted to throw out so that everybody kind of gets your take on it. And this is going back to the 6.7 Cummins we've referenced a few times here. The 6.7 Cummins, there's all this conflicting information. Should we replace the whole turbo? Can we get away with just doing the actuator? Some say you can't, some say you can. What's the story on that? What do we need to do when it comes to these 6.7 Cummins turbos and the actuator?
Well, the fact is, Corey, the actuator is available separate from the turbo itself. In fact, I actually have one here in front of me. The actuator would actually sit right here, and you can get those actuators, and again, you can replace them. Some shops have had a measure of success in replacing them, but there's a couple of pitfalls to keep in mind. You see, we have this gear mechanism right here that actually drives that VGT plate in and out. The actuator, of course, has a motor with a gear that would drive that plate in and out. Well, one big issue, one big failure that the actuators have had is a failure of the motor inside of the actuator. So now that brings the question, well, what caused the motor failure? Could it be something binding with this VGT plate? These turbos, of course, are subject to carbon and other issues that can actually cause that VGT plate to bind. The other issue is, assuming you don't have that problem and you're going to install an actuator, well, we have to have the right scan tool in order to be able to properly synchronize the new actuator and properly align it. Of course, that also requires the proper tools in order to be able to accomplish that operation. So there's a number of things to consider with regard to the actuator replacement. So in view of these things, you've got a truck with a few miles on it, it may simply be more advantageous for the technician and for the shop to just go ahead and replace the entire assembly with the actuator already installed on it.
All right, I think that answers that one pretty well. And then this one actually hits pretty close to home, so I'm going to throw this one out there because I've dealt with this on an EcoBoost motor myself, and that is folks are seeing a higher level of vacuum pumps coming in as a failure, and seems to be that when they fail, they're taking out turbos. Is that a very common issue? Again, we've dealt with it here at the training center, and we actually have a case study on it, and I've dealt with it personally on a vehicle. So, that's two examples right there. What's your take on the vacuum pumps? Yeah, there are some pattern failures when it comes to those vacuum pumps, particularly with the 1.5 liter EcoBoost, that mechanical vacuum pump that it's actually camshaft driven. We've seen some of those actually lock up. There's actually a breakaway that the drive mechanism itself will actually break away and shear off. But we've also seen some issues with regards to internal oil leaks in those vacuum pumps. Now, of course, the vacuum pump sits up higher than the turbo. The turbo's downhill from the vacuum pump. So if there's an internal leak, oil leak inside of the vacuum pump, that oil will have a tendency to run down the vacuum line down to the turbo. And then, of course, the oil gets into the actuator of the turbo, which then destroys the diaphragm of the turbo. So you would be well advised, if you have a turbocharger failure on an EcoBoost, you'd be well advised to check that to make sure that the cause of the failure actually wasn't a problem with the vacuum pump itself, perhaps again developing some kind of an internal oil leak that can cause issues at the actuator. So you may end up with not just the turbo, but also the vacuum pump as well. Yeah, like I say, I know we've dealt with that here, so I agree with you 100% on that one, Darren. And then this one, I think, goes back to the beginning of the class. It's from earlier on in the questions that came through, and I just wanted to hold off until we got to the end here. But the question is, can a restricted catalytic converter cause turbocharger failure symptoms? Not the failure, but symptoms.
Yeah, very much. In fact, we've actually seen several situations. Again, that case study that we opened with, we don't believe, or the technician come to believe, that it probably didn't need a catalytic converter in retrospect. But it is possible for you to have a restricted catalytic converter that would actually cause a lack or impedance of exhaust flow which then in turn robs the turbo of its source of energy. And so we've seen that on not only gas engines, diesel engines alike. We've seen that happen quite a few times. So it is a possibility. You may have that P0299 code. You may have a turbo that's not operating properly, or maybe that it doesn't have the needed exhaust energy to be able to spool the turbo up, and it could be some sort of a restriction in the exhaust, most likely the catalytic converter, if that's the case.
Sounds like a situation where we need to monitor quite a few data PIDs before we start, taking $1,000 parts off the car, right? All right, well, Darren, with that, again, in the spirit of time, I'm going to hold it to that and say thank you for being here with us, and thank everybody else for being here with us. We appreciate you taking time out of your day, especially at the lunch hour here. So we do appreciate you joining in with us. And Darren, I'll let you take us away. Thanks again for being here, sir.
All right, thanks very much for attending our class, Turbochargers. We very much appreciate you attending our class, and we look forward to having you attend future classes, which will be coming up.